All right, the exponential mechanism, I gave you a large promise, like I said earlier, that it can turn a non-private mechanism into a private mechanism, but how does it work? Okay, so one thing I want to mention that people have shown that any function of an epsilon differentially private algorithm also satisfies epsilon differential privacy. Okay, so this is actually one of the foundations that all of this work is based on, because, well, imagine our goal is to generate synthetic data, right? Differentially private synthetic data. And if we are able to generate first differentially private parameters, then from the sampling model, because sampling model at the end of the day is actually a function of the parameter, right? So the sampling model that we apply on top of that will also satisfy differential privacy, okay? So really, this sentence, in our context, we should understand it in a way that if parameters, model parameters, satisfy epsilon differential privacy, then synthetic data generated based on this epsilon differentially private parameters are also differentially private. Okay, so equation 5 and 6, I just put it together. Like, don't overread it too much. What I was trying to show you, okay, typo, sorry about that. Think about this as G, okay? I was trying to say that, think about this as a mechanism, okay, that we're generating the parameters. We name them theta hat as the differentially private parameters, okay? So think about G is the mechanism that makes parameter draws theta hat differentially private. And then F is the sampling model. Let's just say in the simple linear regression that I mentioned to you before, that if the parameter, in this case, I guess, is the regression coefficients, right? The regression coefficients will be the theta, I guess, regression like the betas as well as the sigmas in the normal regression model. Then if we're able to figure out a way to make 5 happen, right? If we're able to figure out how to make those parameters differentially private, then any kind of sampling model like F generically here, once we have those theta hat, we're able to generate synthetic data from it, which will also satisfy differential privacy. Okay, so in fact, I should mention when we talked about, should be able to get back to that, when we talked about the, I think here, right? So here we are able to, if you remember the step, right? The process is that we get theta star from equation 1, and then from y star from equation 2. Okay, so actually going from equation 1 to equation 2, that is also following the result that I showed you earlier, that any function of differentially private parameters will also be differentially private. Okay, as you can see here, equation 1 is trying to make sure that theta itself, okay, will be differentially private once we have this condition satisfied. Then with the theta star that we get, any kind of synthetic data that you generate, in this case it's a table, right, based on the multinomial function here, that once you generate differentially private theta star, you're able to generate differentially private y star. Okay, so similar story, okay, except earlier we didn't get the chance to emphasize it too much. But anyway, so here on the microdata, in the context of micro level data, we also think about it in the same way. Like you can think of equation 5 as a mechanism that we're going to talk about how to make it work. And then equation 6 will be, well, if I have like 1,000 different consumer units, I'm trying to synthesize differentially private income for each of the observation. What I do is I get the theta hat, right, from equation 5, which we will show you how to get it done. And then from there, we just do a simple linear regression draw, right? We get the beta hat, in this case, the beta hat, the sigma hat, and then we have our predictors, and then we get our synthetic data, which will be differentially private as well, okay? So that's the background, and exponential mechanism is what equation 5 is about, okay? How can we make a non-private parameter draw like theta, or draws theta, to be theta hat, which are going to be differentially private. Okay, so that's the question. Well, I wouldn't ask you all to discuss how to do it. This is definitely a very advanced topic. And I want to mention that the EM, the exponential mechanism, is trying to do that, as what we are talking about. Okay, EM was proposed, more than a decade ago But when it was first proposed, I think people, again, were trying to use it mostly for adding noise, okay? But in the context of generate differentially private synthetic data from a Bayesian perspective, what we're trying to do, I'm going to follow a framework proposed by a group of researchers a lot recent than 2007, okay? So this is the general framework, okay, equation 7. So the exponential mechanism generates private parameters that I had from this equation, okay? So we call it exponential mechanism, or they call it exponential mechanism because they are using exponential function here, okay? And what they're doing is, okay, epsilon is still the privacy budget, okay? They define a utility function, which don't worry about it for now, it's the U here, okay? As you can see, utility function is a function about the data and it's a function about the parameter, okay? One thing you can think is, likelihood function is like this, okay? It's about the data and it's also about the parameter, okay? So they have that part. They also have this delta U, okay? So earlier, as we were doing the recap, I highlighted the delta F that we used before, okay? Which is for the sensitivity, right? The sensitivity of the query F, function F, okay? There I was saying that, okay, in this lecture, we're not going to talk about delta F anymore, but we still have delta. Sensitivity is still a key in differential privacy, okay? So instead of talking about delta F, about a function, we're talking about the sensitivity of the utility function, okay? The utility function is defined above here, which we're gonna talk about it soon as well. But the general setup of the EM includes the utility function as well as its sensitivity, okay? And lastly, there is this pi theta, okay? It is the base distribution to ensure proper density function. And in the Bayesian perspective, you can think of it as the prior, okay? So if you look at equation 7, okay, just look at the exponential mechanism itself. What this is doing, as you can see, is that we are utilizing a utility function, which is to be defined and to be constructed, okay? But if we have that, if we also know our exponential, we also know our epsilon, the privacy budget, and then we also know the sensitivity associated, right, with the utility function. And if we have a prior about theta, we're able to generate drops from this equation 7. Okay, so that's the gist of what EM is doing. Okay, so you can think of that you already have, say, certain draws about theta from somewhere, right? They are not private yet. They do not satisfy differential privacy, okay? However, you can turn them into this theta hat, okay? So the question now becomes, how can we find the utility function, right? What will be good utility functions to use? And if we define a utility function, how can we get its sensitivity? And I should say if and how can we get the sensitivity, and then how to make the draws. Okay, so that's what we mean by the EM generates private parameters from a non-private mechanism. Okay, theta itself, it might not be private, okay, but we're trying to get private draws because by the result that we showed you earlier on the slide, on the previous slide, that if parameters are differentially private, then functions of them, which means synthetic data generated based on the parameters, will also be differentially private, okay? So the utility function, let me just refresh your memory a little bit. When we first introduced the differential privacy overview, okay, we talked about delta F is the L1 sensitivity, okay, of a query function, okay? Back then, we are talking about delta F. The sensitivity at the end of the day is always the maximum change in the function F on X and Y, okay? So back then, we're looking at databases X and Y, right? They are having the same dimension. They're different by 1. So if you remember this notation, this is the Hamming 1 distance. Okay, so this is the Hamming distance, and then we're talking about Hamming 1, meaning that X and Y differ by only 1 record. Okay, so that's what we defined it before. Here we turn delta F to be delta U here, and U is the global, U is the utility, and then delta U, we also call it the sensitivity or the global sensitivity, okay? It is defined, okay, as the maximum change in the utility function, as you can see. It's very similar to what we did earlier with the delta F, okay? However, here we're defining X and Y slightly different now. We're using this notation, okay, to indicate that X and Y, they're databases, okay? And they have n records, okay? Both of them have n records, okay? They're only differing by a single observation. So we still have the hanging one distances we indicated here, okay? More formally, in equation 8, we can express the delta U, okay? This is just mathematically what we mean by as the maximum change in the utility function when X and Y differ by only one single record, okay? So we're looking at the maximum change, the supremum, given all of the X and Y or Y when they differ by one record, okay? And over the parameter space, we're looking at the L1 norm, okay? We're looking at the different distance between U, the utility function when you have supply X and when you have supply Y, okay? So see the analogy here, it's very similar. The utility function and then the delta U, the sensitivity itself follows from before, okay? All right, so just a quick summary of the EM. We wish to generate private theta from which we can ultimately generate and release private X, okay? The EM can help us, right? It defines the distribution from which private samples theta hat can be simulated. And then the keys to the EM mechanism are the utility function, what they are, what it could be, and then its global sensitivity delta U, how can we compute it? Okay. So next, we're going to introduce 3 mechanisms based on the EM to generate differentially private synthetic microdata.